Okay, so I promised you that we would use curved arrows for the whole semester. And I also promised you that if you understand them, then it's going to make some things be much clearer, right? So let's practice curved arrow notations with respect to acid-base reactions, okay? The making and breaking of bonds involves electron movement. Of course, that is chemistry, right? That's the whole thing of chemistry. So we use curved arrows to show how these electrons go, right? Now, let me get my marker out here. Seems like I get used to having that ready. So here we see that you have a lone pair of electrons, and this is your base. The lone pair of electrons is always going to be attacking a positive center. That's what lone pairs of electrons do, right? When there's a reaction. So these guys come here, boom, attack that. Now hydrogen cannot have two bonds, so at the same time, those electrons go off onto the conjugate base. Okay, so here was a base, here was an acid, here was a conjugate acid, and here was a conjugate base, right? Now, learning to draw mechanisms like this is super useful, and so we're going to do it ad nauseum. All right, so let's look at a specific example. So here we have, let's say, sodium hydroxide. You know, if you've got sodium hydroxide, how do you spell N? If you've got sodium hydroxide, where am I? Right? And if it's aqueous, what that aqueous really means is you've got some sodium ions somewhere in the bucket and some hydroxide ions somewhere else in the bucket, right? And they don't even know where the other guy is, right? So this then, for example, is sodium hydroxide. So where the sodium someplace else, right? So you've got your lone pair of electrons here. You know this is a base. You know this is an acid. This is acetic acid. So what happens is these electrons come and attack that proton always. Get used to it. Love it. It's going to really serve you well. And can you see if I've got a hydroxide and I'm adding an H to it, it's going to become the conjugate acid of hydroxide, right? Which is H2O, okay? These electrons then, of course, at the same time, it's called concerted. It's happening at the same time. They're happening in concert. Oops, lost my screen. Just a second here, lost my screen. Okay, happening in concert. And so these two happen at the same time. We have to draw them at the same time too, right? You can't draw them in separate pictures. So when that happens, these lone pair of electrons come back onto that oxygen, and we have the conjugate base, which is acetate, an old friend of ours, okay? Oh, by the way, you may be looking at that and going, oh, I bet this guy's about to go into resonance. That's why this is a good acid, because it's resonance stabilized, right? Can you see that? That's what's going to happen there with him, okay? So the base, again, let's look at our little checklist here. The base attacks the acid, as we expected. The acid cannot lose its proton without the base taking it. It all happens in one step, which I'm going to call concerted. And the mechanism shows two arrows indicating the two pairs of electrons move simultaneously. It's concerted. All right. So we're going to use this many, many times. So here's a multi-step mechanism, and this is going to seem a little complicated because it comes from, actually, this comes from organic 2. But you'll see, if you can appreciate curved arrow notation, you're already in a position to appreciate what's going on here. I have an acid. I know it's an acid because it's hydronium. I know hydronium is an acid. And I have an alcohol here, which is going to act as a base. Boom, that comes here and attacks that proton. The bonding electrons come over here and go onto the oxygen, and I'm left with water, right? So the water goes off. Now, then, in this reaction, which we're not going to get this until organic 2, we're going to say, oh, wow, if I just have these guys leave right now, that'll also be a water molecule, right? So these electrons go off on that, and it leaves a water molecule. And can you see if those electrons leave, it's going to leave a carbocation in its place, right? There's the carbocation. And then another water molecule. This is a cool reaction. We're a long ways away from loving it, owning it, but it's cool. The water then comes and takes that hydrogen, and that goes off here. And then we're left with a double bond, okay? So let me emphasize here. You're going to be drawing mechanisms like this yourself before long. But for now, just make sure you understand those arrows, and you'll be ready to do some really sophisticated stuff.